Sharif sir, would you please check, I mean, the slide is okay or not? Share your slide, please. You have to
Yeah,
share your screen, I think.
Yeah,
Sharif
I'm
sir.
doing it. Yeah, just a second. Is it okay? Can you see the screen? Hello?
Yes, sir, we can share, we can see your screen properly.
Okay, great.
It's fine.
Fantastic. So should I keep it like this, or you want me to unshare it again?
Sir, I would like to request the other speaker to share their screen as well, so
Okay.
that, I mean,
So
we
I can
actually
unshare it, right? Stop
unshare
sharing.
your screen, right, sir?
Yeah. Okay, good.
So, আপনার শেয়ারিং এর পাওয়ার আমি দিতে বলতেছি, আমি জাস্ট একটু চেক করতেছি, আপনাকে দিতে বলতেছি আমি শামিনকে। ওকে ওকে
স্যার, সবাইকে শেয়ারিং পাওয়ার দেওয়া হয়ে গেছে, তিনজন, আমাদের তিনজন।
আচ্ছা ঠিক আছে, শরীফ স্যারকে।
শরীফ স্যার আরেকবার যদি ট্রাই করতেন, এটা স্টপ শেয়ারিং করতে হবে।
আচ্ছা ঠিক আছে, বলতেছি স্যার।
শরীফ স্যার এখন যদি একবার ট্রাই করতেন। স্যার এসেছে।
হ্যালো শামিন।
জি স্যার।
আচ্ছা, রাজেক স্যার তো এসছে তাই না?
জি স্যার।
আচ্ছা ঠিক আছে, ওকে
ওকে।
সামিন ব্যাকগ্রাউন্ডটা শেয়ার করুন। হ্যালো, আসসালামু আলাইকুম স্যার। সামিন, হ্যালো সামিন,
জি স্যার।
ওই রাজাক স্যারের মাইক্রোফোনটা একটু টেস্ট করেন তো।
আচ্ছা
অন।
ঠিক আছে।
It's okay, thank you.
Am I audible?
Yes,
Okay. Hello everyone. Greetings from the IEEE Computer Society Bangladesh chapter. The COVID-19 pandemic has a gigantic impact on our daily life. More than half of the global population is under coronavirus lockdown. Public gathering restrictions are implied to slow down the spread of the infection. Considering the current circumstances, the IEEE Computer Society Bangladesh chapter has organized this lecture series on fight against COVID-19 pandemic using machine learning to share the knowledge and ongoing research of experts around the globe with our CS members. The main purpose of this lecture series is to introduce the research challenge and increase the research interest among the prospective researcher. This lecture series consists of 4 lectures. This is the lecture 1. Our speakers are Professor Sajal K of Missouri University of Science and Technology, USA. The second speaker is Dr. Mufti Mahmood, Nottingham Trent University, UK. The third speaker is Professor Dr. Mohammad Sharifuddin, Department of Computer Science, Jahangirnagar University, Bangladesh. Our second lecture will held on 31st May 2020. The first speaker is Professor Dr. M. Sohel Rahman, Department of Computer Science and Engineering, Bangladesh University of Engineering and Technology, Bangladesh. Supapadi Aramdit, Chulalongkorn University, Thailand. And the third speaker is Mohammad Enamul Chaudhuri of Qatar University. On the third lecture, the first speaker is Nilanjan De, Techno India College of Technology, India. Second speaker is M. Atikur Rahman Ahad, Department of IEEE, Dhaka University. And third speaker is Dr. Marzia Haq Tania, School of Engineering and Medical Sciences, Anglia Ruskin University, United Kingdom. And the fourth lecture will held on 14 June 2020. The first speaker is Professor Alamgir Hussain, Healthcare Innovation Center, Teesside University, United Kingdom. The second speaker is Professor Shahadat Hussain, Department of Computer Science and Engineering, Chittagong University. And third speaker is our chair, Professor Dr. Abdul Razak. At this stage, I would like to request Professor Abdul Razak, Chair of Bangladesh Computer Society Bangladesh chapter, to say a few words and moderate the session.
thank you, Professor Shabim Kaiser, for your nice introduction. On behalf of IEEE Computer Society Bangladesh chapter, I too welcome you all to this international lecture series titled Fight Against COVID-19 Pandemic Using Machine Learning. I do believe that it's a very timely initiative taken by IEEE Computer Society executive members. I do highly appreciate our distinguished speakers from different countries of the world to be here to spend their valuable time in front of young scientists and engineers. And I do also extend my sincere thanks to Professor Shamim Kaisar for leading this initiative. So today we will hear from our speakers. As you already know, our first speaker is Professor Dr. Sajal K, then Dr. Mufti Mahmood, and Professor Dr. Sharifuddin. So I would like to first call upon Professor Dr. Sajal K. I would like to briefly introduce his biography, Dr. Sajal K is a professor of computer science and Daniel Chair endowed chair at Missouri University of Science and Technology during 2008 to 11. He was a program director at NSF. Prior to 2013, he was a University Distinguished Scholar, Professor of Computer Science and Engineering, and founding director of Truman Laboratory at UT Arlington, and a professor of computer science at University of North Texas. Dr. Dash is an IEEE Fellow. He published 600 plus papers, 52 book chapters, 5 US patents, and 4 books on smart environments. He is a recipient of IEEE Computer Society's Technical Achievement Award for pioneering contributions to sensor networks and mobile computing, IEEE Region 5 Outstanding Engineering Education Award, and 10 Best Paper Awards. He received Graduate Dean's Award for Excellence in Mentoring Doctoral Students, Lockheed Martin Teaching Excellence Award, Academy of Distinguished Scholars Award, and founding editor-in-chief of Participant Mobile Computing Journal, and associate editor of IEEE Transactions on Mobile Computing, ASM Transactions on Sensor Networks, among others. He served as general and program chair of numerous IEEE and ASM conferences. Professor Dash has been a very good friend of ours, and he has supervised a good number of PhD students from Bangladesh. So in December, he visited Bangladesh and talked in a conference. So I believe many of you are already been introduced with him. And may I call now Professor Dr. Sajal K to deliver your lecture, please.
Thank you, Professor Razak, for the nice introduction. So let me share my screen first, then I'll talk. Okay. Did you co-host me, or is gone now?
I saw you as co-host.
It was there before, but
Yeah, sir, you are co-host, still co-host.
Still co-host, okay.
Right, sir.
But somehow, like that, I cannot share the screen anymore. I did that before.
I mean, could you please check if there is any change?
Sir, try again now.
Sir, would you please try again?
Let me try.
Yeah.
Because earlier I checked and it worked, right? So. Just 1 second.
Yes, sir, it's coming.
It's
Yeah.
coming now, right?
Yes, sir. Yes, sir.
Good. All right. So শুভ সকাল, সুপ্রভাত আপনাদের সবাইকে. Professor Razak, thank you very much for kind invitation. So let me start what I have in mind. Is the screen visible?
Yes.
Yes, sir, your screen is visible. Yeah.
And am I audible?
Yes, you can make it in presentation mode. Then it
Okay.
will be more visible. Yeah.
Okay, I'll do that. Is it okay now?
Yes, sir, perfect. So please go ahead.
Fantastic. So thank you very much for organizing this event. It's really very timely, and we all are very sensitive about this pandemic. Since this is the first talk, I know the whole theme is fighting against COVID-19 pandemic using machine learning. But since this is the first talk of this series, I take this opportunity to introduce some of the basic concepts of epidemic modeling as well as the coronavirus. And then at the end, I'll actually give some directions that what are the machine learning challenges that we can think of. So this talk will not have much of the machine learning, but we'll have a comprehensive understanding of coronavirus or COVID-19 as such, okay? How much time do I have altogether?
It's around 25 minutes altogether.
Fantastic, fantastic. So please, yeah, knock me if I shoot over the time, okay? So the title that I have given is Modeling COVID-19 Pandemic Spread and Human Interventions. So let's first distinguish between disease and virus, because what we have right now is COVID-19, that is called coronavirus disease 2019. But it is caused by this virus, which is SARS-CoV-2, and SARS stands for Severe Acute Respiratory Syndrome Coronavirus 2. It's a respiratory disease. So this is the virus. And the virus basically leads to the disease. And what you see on the right side, this coronavirus looks like a corona. The size of this virus is mean, or the median is about 120 nanometer. So in general, the viruses could be 20 to 300 nanometer size. It's much smaller than bacteria. Bacteria could be 1 to 5 micrometer. So it's very tiny, and one can actually look into the nanoparticle aspect and the chemistry of it, and as well as the medical context, clinical context, but we'll be talking more on the computer science and modeling aspect. Now, World Health Organization, as we know, declared in January 2020 that this novel coronavirus is pandemic, implying a global health emergency. And as of now, more than 4.7 million people worldwide have been affected. As of this evening, 313,260 people have died, and it has spread over 215 countries. Of course, the growth rate at the very beginning was very, very fast because nobody had any understanding what it means. Now, if that growth rate continued without any intervention, then by this year, almost everybody on earth would have been infected. But that is not going to be the case because, first of all, there are good modeling, data-driven modeling, and in which there is a lot of opportunity to apply data analytics, machine learning, AI type of thing, and as well as lots of human intervention. As we know, the lockdown and everything is going on. Now, there are different modes of transmission of this particular disease, the SARS coronavirus. First of all, it is airborne, and which it basically means that through small droplets called aerosols, it can be infected. And some of them are obvious in some way, like we call it symptomatic through coughing and sneezing. But there are also cases where people are asymptomatic, and those are the more benign and hidden, and very difficult to even understand and detect through talking and breathing. Then some people do not show the symptom, even by testing. It gives a false alarm. And then, of course, in addition to airborne, it could also be through direct contact, like handshaking, kissing, or indirect through touching objects or doorknobs, tables, because if somebody who is infected and has touched those surfaces, then somebody can also get infected. So this is the scenario, but the SARS-CoV-2 virus versus the disease, which is COVID-19. Now, this chart, you may have seen it. This is the very latest because I just put this one half an hour ago from Worldometer. And you can all take a look, Worldometer, if you just Google. It gives a very nice statistics every day updated. What I've listed over here, the worldwide numbers, there's no need to go over in all details, but more than 4.7 million people are infected, more than 300,000 people have lost their lives. And USA is the major share of this epidemic or pandemic. I've listed over here the Indian subcontinent. The India situation is growing there, very alarming. But it seems that in Bangladesh, things are very much in control so far. The numbers are there, but the casualties are still very low. And the infections does not seem to be increasing at greater rate. And I hope that it stays under control like that. India is trying very best by putting the whole country in lockdown, but still things are increasing very rapidly. So we have to see in the next 2 weeks what happens. So this is a chart where you see the distribution of this pandemic throughout the different countries. Almost like 30% or a little more than 30% is for the US. So I had actually plotted this chart because a couple of my students are working on this COVID-19 modeling and different kinds of stuff. But this particular plot was drawn on April 25th. So, but it shows the exponential nature of the growth that you can see. Now, in the last 3 weeks, since 25th of April, things have been even escalated much more. And this is just the histogram plot that you can see. US has the largest number, but this is as of April 25th. And here it basically shows the relative chart of the total number of infections over different weeks. And US is right over here, the green, and then the other countries are right there. Now, what it means that when you have any pandemic or epidemic, so there are different types of models, and these models have been there for ages, for the last 40, 50 years. Mostly based on differential equations. Macro model, mostly the population model, but in computer science, we have an opportunity to use different types of devices like smartphones to track contacts and spread, as well as to do more fine-grained data analytics, and where finding patterns, machine learning, AI will be very useful. But nevertheless, a good disease model or epidemic model can actually give very good indication how things are progressing in terms of spread of the pandemic or epidemic, and what are the underlying risks, and containment is also possible through that mechanism. Okay. Now, different types of epidemic models are there. The more popular one is called deterministic epidemic model, where things are modeled based on the number of people in the population who are susceptible or infected or recovered. So it's called SIR model. We'll talk about that a little bit. Mostly it is differential equation based, but there is also taken into picture. For example, when an evolving pandemic like COVID, things are changing almost every other day. So lots of uncertainty is there, and the uncertainty can be captured through this randomness. And when uncertainty is there, the statistical learning also can play a significant role. So when I talk about the model, what I want everybody to get is that there are lots of opportunity for computer scientists and engineers to develop models, which are fine-grained models, data-driven models, based on learning, based on classification. Although I'll not be talking in particular any of them, but it should be apparent. Okay. Now, the two most popular models are called CIS model and SIR model. So CIS is basically susceptible, infected, susceptible. And these are mostly common for repeated infections type of thing, where the model basically reaches some equilibrium endemic. And we'll talk about what endemic and pandemic means. And the SIR model is most of the virus infections are. So these are more bacterial infection, and here's more viral infections. Could be measles, flu, SARS, the previous version of this SARS-CoV-2, which was in 2003, and then COVID-19. Now, what happens? This spread is through mostly the contacts, and the contacts could be the proximity up to a distance of, for example, COVID-19, although we say the social distancing should be 6 feet, but actually it has been shown that it could be up to 12 feet. That's a much more safer, or the safer distance that you have to maintain. Very quickly, the model, I'll not go into the details of that. We are actually looking into many variations of that. In the SIR model, which is more popular for the virus, which is for coronavirus. So basically, a population or anybody, individual from susceptible state, it can go to the infected state if they get the virus, and then could be in the recovery stage. Or they can get it back again, which are very rare so far, the repeated occurrences, right? So this transition from susceptible to infection has some rate called infection rate. So similarly, from infection to recovery also could be another rate is there. So there are different simple differential equations are there that one can look into. We actually plotted this also based on certain data that is available for the SIR model. And you can see that this basically gives, based on this SIR model, the infected cases, fatal means they're all diseased cases, and the recovery case. But what we learned from, and this is the relative chart for different countries. You can see that it was just plotted a couple of days ago. US is a very large number that happened. And then, of course, the other countries are also listed over here with the color code. Now, what does this model say? This model actually does not incorporate any human interventions, such as lockdown, which is the current situation, very unprecedented, social distancing, or vaccination. Vaccination to some extent can be incorporated in SIR model, and I'll actually show that, or let's say face mask or something like that. Okay? Similarly, as I mentioned, that most of these models are deterministic model, but for a dynamically evolving situation like a pandemic like COVID-19, it should be more stochastic model, and there has been a lot of work on the stochastic model as well, but not on the fine-grained data-driven side. And very difficult because to handle the asymptomatic cases, because we don't have enough data from the past, because 1918 flu was long ago and we did not have the technology to capture many data. Now, what happens when you have the vaccination as one of the interventions? So I'll actually talk about a few of these interventions, what happens. And we have actually done some little study, social distancing, what is the impact of that, impact of the lockdown as well for different graded lockdown. So for example, if you can think about your SIR model, and you can also inject vaccination as another component over there. And if you do that, then the equation changes a little bit, the SIR model, the differential equation changes. But what you see in the chart over here, the green line is no vaccination, red line is vaccination. And on the vertical axis, you see the fraction of the population infected over time. And necessarily, with vaccination, the fraction can be, the percentage of infection can be reduced significantly. But as we know, for coronavirus, novel coronavirus, there is no vaccination yet. So at this time, vaccination is not an option. And this particular one shows non-pharmaceutical intervention. That means it's not vaccination. And so social distancing, for example, limiting the public gathering, maybe not more than 2 or 3 people at a certain distance. So large gathering is not allowed. So if you do our university campus closing, schools, campuses are all closed, offices are closed. So in that case, you can see the number of people infected has different possibilities based on the intervention. This is just for the US, because we had the data to run for the US. So another important component is that how does the contact network work? How people get infected, right? And it can be measured to some extent. So there's a notion called reproduction number, which measures how contagious a disease is. For example, if, let's say, it is not contagious, then a person who gets infected will not infect anybody else. And this reproduction number, R0, could be between 0 to any other number as well. It could be positive number greater than 1. If R0 is 1, that means one person can infect another person. So that leads to endemic. But cases like COVID has actually the infection rate more than 1. That means reproduction number is more than 1. This is, I'm just showing as a 2, but when the reproduction number is 2, but in general, for COVID, it is between 3 and 4. So that basically means it leads to a pandemic. It's a more serious situation because exponential growth can be observed very quickly. So you can see the different types of viruses that you can think of: SARS, or smallpox, chickenpox, and flu, measles, and everything. So COVID's, this reproduction rate is between 2 to 4. And in some cases, it has been shown between 3 to 5, but 2 to 4 is kind of median. So you can see that's why the exponential growth is observed. Even in 2-3 weeks' time, things can escalate so much. We also ran some data sets to generate the contact network out of this COVID-19 data that you have from CDC, World Health Organization, Johns Hopkins Medical School. But the tool that we used, so this is what we did not do. This was a tool that was developed for the school children's contact in 2010-11 timeframe. But we used that tool to basically see what happens if we take some of the parameters from the COVID-19 data. So the number of nodes of the people that we considered in our little experiment is 236. Number of links or the edges, people interacting is about 6,000. And then the transmission rate we assumed is quite high, like 30%. Recovery rate is even much higher because more people can get infected, but casualties are much lower compared to the total number of recovery that we have. And so we did some experiments, and I'll show you some results. So for example, if I take the epidemic SIR model, then I can generate a contact network based on what happens. Now, these links that you see, that may not be deterministic, it could also be probabilistic. So this graph could also be a probabilistic graph, okay? Now, once you throw the stochastic nature of it, then of course differential equation also becomes a little bit more complicated, but one can handle it. But for the sake of this discussion, we can assume that for a given population, when they get infected, I can generate a contact network. And the contact network has a lot of property of a complex network. So we did some experiments for the same situation, like 236 individual, about 6,000 ages and all, assuming different infection probability rate and different types of recovery rate. So you can see the number of people infected. I can actually control that based on the transmission rate probability. So 10% transmission, 30%, very high, like 100% probability. And this particular chart shows that when I control the gamma, gamma is the recovery rate. So that means, so I can actually generate different types of chart based on the model and taking actual data sets for the contact networks. And good thing is that right now, although we may not have huge number of repeated data to learn, but still huge number of data is being collected everywhere by CDC in the US, Center for Disease Control, World Health Organization, Johns Hopkins Medical Center, many other. Every country is doing that, which is very good. That will give a rich collection of data to play with. Now, how does the social distance play a role? So we also looked into that. So this basically, so it shows two things. One is social distance and the lockdown. So because lockdown implies the social distance is increasing. So we consider lockdown, let's say 25% of the population is under lockdown for a country, or 50% of the population, or 75% of the entire country is locked down, just like in India, for example. You can also see the number of infections, and that actually grows, reduces over time. So this is the kind of growth that you can see. One can actually model, give the equations corresponding to that. We also looked into the clustering, and clustering, of course, has a lot of things to do, classification and clustering with machine learning that you know. So we wanted to find out which community or the cluster of people have high susceptibility to spread the infection, okay? So you can do lots of little experiments with known tools and techniques of machine learning and AI to understand what is happening, and the data set is becoming richer and richer. We looked into the contact network from a graph theoretic perspective, look into different, as a complex network, like different types of centrality measures. And I'm not actually going into the details of these things, but centrality measure is a very well-defined terminology based on the degree connectivity, based on the number of paths that you have. One can define the betweenness centrality, degree centrality, close centrality, edge centrality. And these are the different types of complex network that can be generated from the coronavirus contact network, for example. Now, the theme of this particular series of talks that you have organized is fight against COVID-19, role of machine learning. So given that we understand a little bit of the modeling of the any epidemic or pandemic, as well as the kind of data that are being collected. So these are the different things that one can think of. How do you cluster groups of people in the contact network? They are highly susceptible, or they are less dangerous type of thing. In terms of infection, okay? So classification clustering and that is in the purview of machine learning, data analytics type of thing. You can also look into the deep learning concepts like CNN, convolutional neural network, or recurrent neural network type of thing, to understand that how to, for example, if I want to do the containment of this spread of the disease, want to understand how to do more fine-grained data analytics kind of stuff, then one can look into the deep neural networks type of learning. And when you do any type of machine learning, hyperparameter optimization becomes an important research concept over there. I do not know yet, but the question would be that could machine learning and AI help to isolate and detect the asymptomatic cases? Because those are the ones where people don't show the symptom, or they develop the antibody or whatever, but other people can get infected who are more vulnerable, right? And in the US, things are opening slowly. In different countries, the business is opening. Italy also is doing so. But I think the continuous testing, contact tracing, and mitigation strategies will be required. Even to do that in a large scale, AI machine learning would be of help, because because you may not be able to do testing for everybody in the population, but I want to do probabilistically. Take random samples of the people and do that kind of testing. So where it should actually machine learning AI would be helpful, and contact tracing and the mitigation, different types of mitigation for protection and prevention. Could be wearing the mask, sanitization, social distance. I hope that lockdown does not happen too often for any country to break down the economy. So these are the things that one can actually look into from machine learning perspective, and I'm sure that many of the other speakers from subsequent talks will actually talk many of them. So this is the fight. Basically, we're talking about the fighting against the COVID-19. We are also looking into some game theoretic model. Game theoretic model, why? Because people in general are becoming resistant to lockdown. For example, in the US, it is happening in different cities. Australia also, people are protesting. So that means there's a conflict between public policy and individual incentives. What is people's incentive? Of course, you want to stay healthy, but at the same time, they think, no, I want to go out. I want to have my business type of thing, right? So the societal utility function versus individual utility function has a conflict. And on top of that, there could be social behavioral stuff like fear, for example. So how do you take those into account? So we are actually looking into how to develop strategic games, and mostly looking into price of anarchy type of approach. And we have some lead on that, but we are not ready yet to make any conclusive presentation, because we are still solving the problem. So fighting against the spread can also be looked into a game theoretic approach.
3 more minutes, Professor. 3
Sure.
minutes.
This is my last slide.
Okay, thank you.
Yeah. So basically, the question is that why game theory? Because as I mentioned, there's a public versus a policy or the country's decisions. There's a conflict. So how to resolve those kind of things and reach an equilibrium so that the productivity of the society and individuals could be increased. At the same time, people will be protected from the health conditions. Also, game theory is useful because this recovery and death rates have a time-dependent phenomena, right? So that could also be captured in stochastic games. What we do not even know that how many people are really infected and how many people are going for the testing. So lots of uncertainties there. So in this game or machine learning type of model, the uncertainty plays a significant role. SIR model is a very basic one. There are more sophisticated model called SEIR, but E is the number of people who are exposed, where asymptomatic case may be very benign over there. And then, of course, different types of graph properties that we can exploit for the clustering or finding the more influential node who are prone to infect a lot of other people. Okay. So with that, let me just stop over here. And I do not know whether there's an opportunity for taking questions or whatever is the schedule that you may follow. I'll just go with that.
Thank you, Professor,
Thank you
for
very
your
much for the
nice
opportunity.
presentation. Thank you, Professor. Yes, we will take a few questions. Well, you have rightly identified different models with and without human interventions, SIS and SIR, and you have also related the graph theoretic and the game theoretic approaches with this pandemic situation. Well, we do have some interested participant who raised hand. Shaila Sharmin, question please. Very briefly, directly the question. Shaila Sharmin.
I have to.
Yes, I have noted down, Dr. Atik. Okay, if Shaila Sharmin is not here, then may I request Professor Atik to raise your question. Professor Atik. Samin, is there any problem with microphone?
I'm checking it, sir.
All right. Yeah. Now. Much is okay. So the point is that host has muted all participants, and now it is okay. Can you hear me?
Yes, sir.
Yes, we can hear you.
Okay. Okay. So Professor Sajal, how are you? It's great to be here and get to it's a nice talk. So I have two questions. So I'll give the first one, and then if I get time, I'll go the next one. So the point is that how large the data can be the minimum data to work with this kind of situation. Because of randomness or whatever, we need to consider that medical sectors should agree with our results. So what do you feel? Can you give some idea on what amount of data and what kind of data can be considered for this kind of cases?
Samin, please check microphone of Professor Das.
Can you hear me now?
Yes, yes, Professor.
Yes.
Okay, maybe I was muted. So, so I don't have a definite answer to that. What is an optimal population size or data size that we need to see to get the model working in the right way? We're still in the experimental stage, but you have seen the huge amount of data is becoming available. Sanitization of the data, curation of the data is required still. One is noise, and secondly, what are you looking for? For example, even for contact network that you wanted to build, we can only take 236 people's data, about 6,000 links, because many times the links are not very apparent. So if I want to construct a contact network, this is not easy. Although we have data for a lot of people, but identifying the contact network is still challenging. So we are still doing experimentation, developing the mathematical model, game theoretic model, graph theoretic model. But I think I don't have an answer to your question right now, but those are the things that we'll be looking into. And that's why we think that deep learning may be a useful tool to find out an optimal parameterization. So, yeah, I think we are at the research stage mode. I have seen some publications, but these are very rudimentary type of conclusions right now. And you have another question, right?
Thank you. I mean, if Professor Ajak, can I ask?
Yes, yes, please.
Okay, so another point is that you mentioned in the clustering part that a community having high susceptibility of spread infection. Now, for this kind of community data, how can we get the data? So what kind of information you get as input to decide this kind of spread infection decision or something? So can you give us some idea?
Yeah, the contact network that we built was embedded on top of the SIR model, right? So our contact network is not just a graph model. It had embedded the SIR model. That means we know for that 236 individuals who are infected, who are susceptible, who are recovered type of thing, right? Now, then in the contact network has 236 people, but about 5,800 some number of links. So there are lots of clicks are there, right? So we are basically looking for those clicks, that who are in contact with whom in a more frequent manner than otherwise. So that's the way we are taking the epidemic model in conjunction with the contact network model, and together we are trying to infer which cluster of people of the community is more susceptible or has more probability for infection with each other. And this is happening, for example, in Mumbai, in India, in some of the low housing area, slum area, this has been observed. In Chennai, yesterday they closed down a huge vegetable fruit market because more than 2,000 people got infected, for example, right? So the contact actually, but some of these people, farmers, they come with truckload of vegetables and the fruits from far apart, several 100 kilometers apart. But when they visited there, they got the infection. And when they went back, they infected more people, right? So I think the contact network, that's the one that we are using for tracing, right? You also know that the Google and Apple, they have announced, and many other apps are being coming Bluetooth based, but those are more proximity based. So if you're in the neighborhood, you can actually detect the first order link. But we are looking more as a holistic approach, as a network.
Yeah. Thank you so much, sir.
Thank you, Professor.
Yeah.
I saw here Professor Jahidul Islam, Professor Lafifa Jamal, Professor Sohail Rahman. Do you want to make any comment, Professor Jahid? Professor Jahid. Samin, could you please help him to turn on the microphone?
Sir, now maybe on. Jahidul Islam.
Okay.
Okay. Hello.
Yes, yes, please.
Now I get. Okay. Thank you, Professor Sajal K. After a long time, I'm hearing you.
Fine. Thank you very much. Good to connect with a lot of good friends. Yeah.
Yes. Yes. And this is a very nice talk of you, because this is the situation is going on actually, the COVID-19. So actually, one of my students actually, he predict the maximum doomsday basically. Say in Bangladesh, day by day the number is increasing, but we don't know about the maximum rate of infected. So in your model, can you predict, the doomsday of Bangladesh? That is the maximum infected rate.
So,
okay, thank you. Yeah.
So yeah, so can so basically what is happening? We are taking a data-driven approach, right? So ours is not completely this differential equation based or stochastic differential equation based model. So we are capturing the evolution, dynamic evolution on a fine-grained manner. So we can give a range that within this time frame, the peak will happen, is expected to happen, right? But as you know that, like any other model, even if you see Dr. Anthony Fauci's presentations and panels and all, he's the #1 epidemiologist in the US, works for NIH, he's a public health professional. Even he is sometimes perplexed that whatever you predict does not really happen. Because as I said, like there are many other human intervention components that is difficult to capture in the model, like let's say lockdown, social distancing. You can get a first order model, but exactly the impact of those things and translating that into the equation is not that easy. So flattening the curve is happening because of multiple different reasons, but with conservative estimate, we can give a range. Let's say this is the time frame in which, for example, for India, I can tell this month of May is extremely critical. So beginning of May, the numbers are very low in the thousands. Now you can see 90,000, more than 90,000 have been infected. And these are the official thing. A lot of people have not been tested. Even the casualty rate of about 2,800, that also probably is underestimated. Since people are not tested, whether they're dying out of COVID or something, nobody knows, right? So I think there's a grain of salt there, but models are actually becoming more and more powerful because of this data analytics approach, data-driven approach, different types of fine-grained modeling tools and techniques that you can use. So I cannot tell you, okay, there's a May 25th is the doom day, but I can give you a range of maybe 4 to 5 days time frame. That's a very critical time because the growth rate can be predicted. But when exactly the flattening happens, that depends on multiple things, whether people are complying with it or not. Does that answer your question?
Thank you, Professor Sajal K. You have surely opened up a good number of avenues for further research, and you have at least shown the terminologies, the issues that need to be considered or need to be given importance for further research and so on. I believe our young researchers, scientists will look into it and further find out the ways and means to address this COVID-19 pandemic situation. Thank you very much, Professor Sajal K. for your valuable time for us. Thank you.
Thank you very much. And I may have to probably miss the next lectures because it's 1:45 early morning.
Yes,
Yeah.
yes. Thank you. Thank you. Thank you.
I wanted to attend all of them, but it will be difficult. Okay. Thank you so much for inviting me.
Thank you. Okay. May I now hand